This topic in finite element analysis module is the truss elements. Truss elements is the simplest type of finite elements that we always use to have a segue into the wonderful world of the finite element analysis. Truss elements have lowest degrees of freedom among all the finite elements the types that we are going to look at in this module. Although they are quite simple, they have quite a lot of applications. You will see many structures that can be quite accurately modeled by using truss elements. So let's go together through this journey. At the end of this lecture, you will be able to identify nodes and degrees of freedom of truss elements and structures, explain the concepts of element or local stiffness matrix and a structure or global stiffness matrix, write the equilibrium equation for a truss structures and identify its terms, define boundary conditions and loads, and finally diagnose models with singular stiffness matrix or instability errors. So why do I need to know about this? In reality, pin-jointed structures are everywhere. So here I have shown a picture of a bridge, and this bridge can be modeled by using pin-jointed structures. So here we can assume that all these beams are linked with pins, and therefore we can simplify our analysis. Another example is the London Eye, which is made of different members that are connected by pins, so we can simplify their joints as pins, and therefore we can simplify the modeling, and this simplification is absolutely fine and accurate. Well, we can see other examples here. We can see this little bridge, and this bridge here, I believe this should be the Millennium Bridge. So and this structure as well. So you can see there are several structures in everyday life. If you pay attention, these are structures that can be modeled as pin-jointed structures. The other reason is that truss elements in general are the simplest type of finite elements, but they are very efficient. So by using these type of elements where it is reasonable to use them, as the structures I showed you, you can reduce the computational cost massively. So before starting discussing the theory of truss elements, we need to recap the assumptions in trusses. One of the assumptions we have is that members of a truss are connected by frictionless pin joints. This is a simplification, but a simplification that works really well. Loads and supports occur only at joints. And finally, loads in truss members are purely axial, either in tension or compression. And I'm sure you can work it out yourself why this is the case. If not, just look at the classical mechanics book. So here is the bridge that we have seen. Let's say one side of this bridge, we would like to model it. This is a simplification of that side of the bridge. We have these bars, which we call them truss members, and these bars are joined together by using pins. So I'm sure you know that this is called simply supported support or pin joint support, and this one is a roller support. So what is a truss element? Every truss member can be represented by one truss element. So literally this is a truss element. You can see here, this is the body of the truss element, the element itself, and on either side of this element there is one node, node number 1 and node number 2. A truss element is defined by its length, its cross-sectional area, and the elastic modulus. All right, so let's now zoom in onto one of the truss members. So we can model each truss member with a truss element. For simplicity, we will focus on a truss element that has only 1 degree of freedom at each node. So let's draw a truss element which is defined by 2 nodes. This is node number 1. This is node number 2. And we are assuming that this is our coordinate system, x and y. So as I mentioned, we are assuming we are working in 1 degree of freedom. So this means that each node can displace only in 1 direction. So here we're assuming that displacement is only possible in the x direction. Okay. So as a result of loading this truss element, we could have displacement of node 1 in x direction. We call this u1. And we could have displacement of node 2, which we call u2. And of course, there has to be forces that will cause these displacements. So the force that is applied on node 1, we call this F1. And the force that is applied on node 2, we call this one F2. All right, now we have the free body diagram of that truss element. You will see later that we will need the length of the truss element as well. So let's call the length L. So this would fully define the dimension of our truss element. And in terms of mechanical properties, so another dimensional property is the cross section of our truss element, which we can call it A. So A would stand for the cross section. So you know what is the cross section? If you do a cross section and you look perpendicular to that, that is the area that you will see. And we assume that this truss is made of a linear elastic material. So for that, we would use Young's modulus to define the mechanical properties of the material. Okay, now what we will do, we will use the equation of static equilibrium in order to find the relationship between these 2 forces. So you know from equation of static equilibrium that sum of the forces in each direction is 0. So for now we focus on the forces in the x direction, which are F1 and F2. So we have F1 plus F2 equals 0. And that will give us F1 equals minus F2. I think that is quite intuitive, right? Because this truss is in static equilibrium, so that force has to be equal to this force, but opposite sign. So that is what this equation is telling us. All right. What we want to do next is to find a relationship between forces and displacements. In order to do that, we need to use our knowledge of mechanics of materials. So from mechanics of materials, we know that there is a relationship between stress and strain. So if we call stress sigma, and this stress is a stress in the normal stress in the x direction, right? Because this is again, 1 degree of freedom system that we're looking at. So that stress will be equal to Young's modulus times strain, right? All right, so we can now start defining the relationship between strain and displacement and stress and force. So for stress and force, we know that force divided by cross-sectional area, that will give us the stress. In terms of strain, we can use the displacement at these 2 nodes to find the elongation, the extension of the truss element, and divide it by dimension L. Okay, so I will do that first here. So this equation will be Young's modulus times strain, which is elongation. That would be U2 minus U1 divided by the original length, which is L. Okay, we have now part of this equation, but the other part is the relationship between stress and force. So in order to find that relationship, we need to look into internal forces in our truss element. Stress is related to the internal force, but F1 and F2, these are external forces. In order to find that relationship, we need to consider an imaginary cross-section. So imagine that we do a cross-section somewhere along the length of this truss element, like here, and that will divide this into two portions. Then we can focus on each of them in turn. So for now, let's focus on this side of the part of the truss element. So if I draw the free body diagram for that side of it, it will look like this, where we have force F1, correct? And then we have an internal force here, which I'm sure you know, that would be sigma times A, right? So that is the definition of stress. Stress is the force divided by area. Hence, the internal force is stress times area. And we do the same thing, the same equation of static equilibrium that we used before. We apply it to this free body diagram. So again, sum of the internal forces in x direction are 0. So that would give us F1 plus sigma A equals 0. And here we have the relationship between F1 and the stress, correct? Now we can do the same thing for the other side of our truss element. So we draw the free body diagram. We have the external force, which is F2, and here we have the internal force, which is sigma A. Well, you may ask why here the direction of the force is opposite to this one. We are assuming that sigma is a normal stress and it has a positive value. That is the assumption. Of course, if the value is negative, it means then internal force is a compressive force and hence it is producing a compressive stress. All right, so this is not tensile anymore. But we assume that the internal stress is a tensile normal stress, and the sign eventually will tell us if it is if the structure is in tension or in compression. So here we are writing again the equation of static equilibrium, and that will be F2. This time that will be minus sigma A equals 0, and that would give us the relationship between F2 and sigma A. Okay, I think we are more or less there. So you can see here we have the relationship between F1 and sigma A, F2 and sigma A, and here we have the relationship between sigma and U1 and U2. So you can imagine what we will do next is that we will then put this relationship, this part of the equation, in this equation and in the other equation. So if you replace sigma with this expression, then we will have the relationship between forces, the external forces, and the displacement at these two nodes. Okay, so let's tidy up the equations that we have found. So as you remember, we are going to replace the stress with the equation we found from the relationship between stress, strain, and elastic modulus. So if I rearrange that equation a little bit, it would look like this. So A cross-sectional area times elastic modulus divided by the length of the element times U1 minus U2, which is displacement at node 1 minus displacement at node 2, equals F1, which is the force that is applied to node number 1. And we have a similar expression for the force that is applied to node number 2. But this time we have U2 minus U1 equals F2. Okay? Well, I think now you see that something is emerging from this work that we have done so far. So if I now write this in a matrix format, you will see that we will find something quite interesting and neat. I'm going to rearrange this and write it in a matrix format. Now you can see I'm introducing a new variable. I call it k, and I explain in a moment what k is. So we have k minus k and minus k, right? Multiplied by a vector. We call it the vector of nodal displacements, which is u1 and u2, and that would be equal to the vector of nodal forces, F1 and F2. So what is K? You can now easily imagine. K is A, which is cross-sectional area, times elastic modulus divided by the length of the element. So I write it here. K equals A, E divided by L. Well, I think this is now really nice and beautiful, right? So you can see now clearly the relationship between the vector of nodal forces, F1, F2, vector of nodal displacement through a matrix that is made of geometrical properties, which is A and L, and material properties of the truss element. We call this matrix the element stiffness matrix because it defines the stiffness of our element, and I can abbreviate this expression into something a bit simpler. So we call it K times D equals R. All right. So we have now an equation that is written in terms of a matrix, vector, and another vector. This is the element stiffness matrix. This is the vector of nodal displacements, and this is the vector of nodal forces. And this is really the essence of a finite element method. So in finite element method, whatever we do, we are trying to find a relationship between displacement and forces, and then always we do the calculations, but finally we summarize everything into a matrix format, very much like what you see here. So it doesn't matter if you are using a truss element, if you're using a beam element that we are introducing next, if you're using a solid element, shell element, etc. It doesn't really matter. At the end, everything will be consolidated into a simple equation like this. What will be different, of course, is what you will have in these vectors and in this matrix. Okay, well, so far we have looked at one truss element, but what if we have more than one truss element? So let's extend what we discussed so far into two truss elements. So I have truss element number 1, okay, and I'm adding another truss element which is just joined to this one at this node, truss element number 2. So this is node number 1, node number 2, node number 3. And well, here you can see I call this node number 2 because these two truss elements, they are sharing that node with each other. We call it a shared node or a common node. And I number this one element number 1, and this one is element number 2. Okay, well, as usual, you can imagine then when this is under loading, there will be some displacement at any of these nodes. So we can call this with the U, so U1, U2, and U3, So these are the displacements, and the forces that are causing these displacements, I'm going to use a different color for the forces this time. So this is force F1, and again I should emphasize these are external forces, not internal. So force F1, force F2, that is directly applied on node number 2, and then we have force F3 that is applied to node number 3. All right, so we have forces, we have displacement, but we also know that our truss elements have geometrical properties that are defined by length and cross-sectional area, and they have material properties. Assuming they are made of a linear elastic material, then the property we use here is Young's modulus, or E. So the stiffness of the element then is written, if you remember from the previous discussion, the stiffness, so we use K here for this stiffness. So ignore this one. So that's K. K1 equals A1 times elastic modulus E1 divided by L1. Okay, so cross-sectional area, Young's modulus, and length. And for the other element, we have K2. That is the stiffness that is defined by cross-sectional area, elastic modulus, and length. And well, you can see here that two elements can have different lengths, they can have different cross-sectional area, even they can be made of different materials. So you can see E1 and E2, like steel and aluminium, for instance. All right, if we write the equation of static equilibrium now for this more complicated structure, and then we simplify everything and solve the simultaneous equations, etc., we will end up with a matrix equation that we can summarize with a K. So here's K. And as usual, we have vector of nodal displacements. So that would be U1, U2, and U3. So K times displacement equals vector of nodal forces. Again, I should emphasize these are external forces. All right. Or we can write it even simpler, like K times D equals R. Okay, well, perhaps you have noticed that here I'm using capital K, I'm using capital D, I'm using capital R. So there is a difference here between this structure and what we saw previously. Previously, we focused on an element and we wrote the equation for the element stiffness matrix. This equation that we are writing is for the structure. This is the equation of equilibrium for the entire structure, and this K is the structure stiffness matrix. D is the vector of nodal displacements, but now includes the entire structure, and R is the vector of nodal forces, again including the entire structure. So your question might be that, okay, well, D and R, we can understand, we know what they are, but how do we find K? Because now this has to combine K1 from element 1, K2 from element 2, or if you have many more elements, like thousands of elements, how can you obtain K, or in other words, how can you assemble K? Well, actually, this is already given. This is provided in finite element packages, but I'm going to show you how K is assembled for this simple finite element. All right, now we want to find the equation for the structural stiffness matrix. Again, I should emphasize we are looking at 1 degree of freedom. We are looking at one dimension, sorry, not 1 degree of freedom. We're looking at one-dimensional displacement, so it's only displacement in X direction here. But we have now degrees of freedom that are 3. So we have 1 degree of freedom here, which is U1. Another degree of freedom is U2, and a third degree of freedom is U3. So the structure has 3 degrees of freedom. So you remember that the vector of nodal displacement and vector of nodal forces, they have now 3 elements, each of them, U1, U2, U3, F1, F2, F3. That means that K matrix, which is the structure stiffness matrix, it has to be a 3 by 3 matrix. So here is K, and it should be 3 by 3. So I give it enough space to put in 3 by 3 elements, so 9 elements into the entire matrix. Well, this part, these first two are related to node and to element number 1, so would be related to node number 1 and 2. So here we can bring in the element structure, element stiffness matrix, and put the components here. So if you remember, the components were K1 and minus K1, minus K1, and K1. Okay, so this is related to degree of freedom U1, this is related to degree of freedom U2, and this one is related to degree of freedom U3. But as you can see, there is no connection between this element and node number 3. All right, so essentially there is no involvement of node number 3 here, and therefore the stiffness related to that would be 0. Okay, so now we have a portion of the K matrix, the structure stiffness matrix, that is related to stiffness of element number 1. We add to this the stiffness of element number 2 in the same way. So here we have, if you remember, U1 is here, U2 is there, and U3 is in this position. So there is no connection between U1 and element number 2, so that would give us 0 here, 0 and 0, and also in this place. And this part of the matrix will be occupied by the element stiffness matrix, so that will be stiffness of element number 2. And this is K2. Okay, well, now you can simply add up these two matrices to give you the structure stiffness matrix. So you know that this added to that, this added to that, and this row added to that row, that gives you the structure stiffness matrix. Well, we have done it for 2 truss elements here, but if you want to extend it to many more truss elements, it is exactly the same thing. We need to position the stiffness of every element in the right location within the structure stiffness matrix, and then we will add up all these sub matrices to obtain the entire stiffness matrix for the structure. This process is called assembly. Okay, well, so far we have been looking at 1 degree of freedom. Now we want to extend this to 2 degrees of freedom. So again, we have our coordinate system. We just draw the coordinate system x, y. And this time we consider a truss element that is not just along x-axis, it is actually tilted. So we have a truss element that would look like this. So again, node numbers, number 1, number 2. In node number 1, now we have displacement in the x direction. So we call this U1. And we have displacement in the y direction. So this time I'm going to use a different convention. So this is V, that is defining displacement in the y direction, and V1 means displacement of node 1 in one y direction. And the same thing for node number 2. So we have U2 and we have V2. Okay, so this completely defines the so-called kinematics, the displacement of the entire element, node number 1 and node number 2. So we also have the corresponding forces for each node. So again, node number 1 and 2, I am just plotting the same element, but not to confuse the forces with displacements. I'm plotting another one here which shows the force in the x direction. I'm calling this one fx1, and the force in the y direction at node 1, this is fx2. Similarly for node, this is fy2, okay. And then similarly for node number 2, this will be fx2, and this will be fy2. All right, so fx1, fy1, I had to correct this, and then fx2, fy2. Okay, now we need to again find the element stiffness matrix. I'm not going to derive everything for you, but I have it written. So essentially, we need to put together the geometry and the material properties into the stiffness matrix, but this time we have an element that is tilted at, let's say, angle alpha. So you can imagine here we are going to use the sine and cosine of alpha to resolve each of these along the axis, and that gives us the element stiffness matrix, which I'm going to write it here now. So that would be K. Again, this is lowercase k because this is the element stiffness matrix. So we will have K times a bigger matrix. Now this matrix is a 4x4 matrix because we have 2 nodes and each node has 2 degrees of freedom. So overall we have 4 degrees of freedom for this element. So here this will be C2 CS minus C2 minus CS, right? And then we have the other elements of this matrix that I'm just going to add here. So S2, and then we have minus CS, and we have minus S squared, and then we have minus C squared, we have minus CS, C squared, CS, and then finally the last row, minus S squared, CS, and S squared. Okay, so this is our element stiffness matrix. So K again is what we had before, which is cross-sectional area times Young's modulus divided by L. So this is our K. And well, C and S, C is cosine of alpha and S is sine of alpha. Okay, so you see that this is, although it's a bit more complicated, it is using like geometrical description of the orientation of the element, length of the element, material properties, cross-sectional area. So this is the sort of things that you will just give to the computer to do it for you. You don't need to do it manually. But what is then interesting out of this is that eventually once you do this, you will have the vector of, you will have the element stiffness matrix, which is K, times the vector of nodal displacements, which is D, and these will be equal to vector of nodal forces, right? So this time you have a matrix that is 4x4 for the stiffness, and you have a vector that is 4x1 for nodal displacements and 4x1 for nodal forces. Okay, so nodal displacements are u1 v1, u2 v2, and nodal forces are fx1 fy1 fx2 fy2. All right, so this is really extending what we have seen in 1 degree of freedom to 2 degrees of freedom, and you can imagine we can just continue that and extend this to 3 degrees of freedom. And I'm sure you can imagine then the size of these vectors and this matrix will just be increased, because if we move to a 3 degrees of freedom, we will have 3-dimensional space, we will have 3 degrees of freedom in node 1 and 3 degrees of freedom in node 2. So that would mean that this vector will be 6 by 1, this vector will be 6 by 1, and this vector will be 6 by 6. So it's really as simple as that. So you just extend this, but all of this has already been written into codes in finite element packages, so you don't need to worry about that. But what you need to know is that any truss element is made of 2 nodes, and in the general sense, which is a 3-dimensional space, each node has 3 degrees of freedom, and then the entire element has 6 degrees of freedom. How about 3D? Okay, so in this case, if we extend this into 3-dimensional space, each node has 3 degrees of freedom, which are translation in X, translation in Y, and translation in Z. And hence, the element stiffness matrix is a 6 by 6 matrix. If I want to write it mathematically, here we go. This is the equilibrium equation. So this is exactly the same as what we've seen in 1D, 2D, and now in 3D. But these matrices have now different number of members or elements. So this one is 6 by 6. This is the vector of nodal displacement. This is the vector of nodal forces. Okay, so far I have shown you the equilibrium equation for the element. I have shown you how it can be assembled to find the equilibrium equation for the entire structure. Now the question is how to solve problems using this method. Okay, do not worry, software will do it for you. But you should define what the software needs to solve this problem. So what are the things that you need to define? You need to define the connectivity between elements or joints. So you remember that those 2 elements were sharing node number 2. So it's important for the software to understand which nodes are shared, etc. The other thing you need to provide is the geometry of different elements, that is length and cross-sectional area, as well as its material properties, which in this case is Young's modulus. You also need to define the boundary conditions. So these are known nodal displacements. For instance, where you have the support, these are known, as well as forces that are applied to joints. These are external forces. So if you know any of these, you need to apply that. So here's a practical problem. It shows a lantern with a support that is a truss structure. And you can see the material properties, the dimensions of the truss members. I have provided a complementary video where this problem is solved by using ANSYS. So it's good if you watch that first and come back to watch the rest of this lecture. Okay, let's look at this problem. Here we have a lantern that we are hanging it from this truss structure. The truss structure is made of 3 truss members. At this location, you can see that this is supported, what we call a simply supported boundary condition, and here is a roller support. So essentially here there is freedom to move in the vertical direction. So let's use our usual coordinate system as well. So X and Y. So at this point, at this joint, it can move in the Y direction, but not in the X direction. Here it cannot move in Y or X direction. And then we have a lantern here that has, let's say, mass M. Okay, now we want to model this using truss elements. In order to do that, so we need to replace every truss member with 1 truss element. So we will have 1 element here, 1 element there, okay, and then we have a final element, the 3rd one, that is at this location. Okay, so we have element number 1, element number 2, and element number 3, right? And then we can give numbers to the nodes here as well. So node number 1, node number 2, and node number 3. Okay, so now we have our finite elements model, right? This is the finite elements model of that structure. So now what we need to consider is external forces and the boundary conditions, because this will determine what is known and what is not known in our vector of nodal displacements and vector of nodal forces. So in node 1, we know that displacement in x and y are 0. So that will be u1 equals v1 equals 0, correct? And in node 3, we know that it cannot move in the x direction, but it's free to move in the y direction. So here, the only degree of freedom that is constrained is u, which is displacement in x direction. In terms of external forces, we know that the external force that we know is this one, right? And this force is the mass times gravitational force. So that will be, if I use the positive convention, so that will be minus mg, right? And then this one, we can call this Fy2, yes? So that is the force applied, external force applied on node number 2 in the y direction. Of course, we have other forces that are external here. One is, two forces are applied on node 1. These are the reaction forces at the support. Also, we have an external force here that is the reaction force at the support in the x direction, okay? So if I throw those two forces, so this will be Fx3, and we have two forces here as well, so this will be Fx1, and this one is Fy1. All right, so these are all the external forces. These are unknown, these three are unknown, and this one is known, and then we have the boundary conditions that we know. Okay, now we want to write the equation of static equilibrium for our finite element model. So we have the structure stiffness matrix that will be timed by the vector of nodal displacements. But now this vector is a long vector. Each node has 3 degrees of freedom, x, y, z displacements. Therefore, this will be a 9 by 1 vector. And I'm going to put in the values that we know of. So u1 is displacement in x direction in node 1, and we know that this is 0. We have v1, this is 0. Well, we are now considering this in the general space, 3D space, and our assumption is that all the degrees of freedom that is perpendicular to the surface, they are fixed. So that means that I can put W, which is displacement in the Z direction, equal to 0. Okay? And I will just continue for node number 2. So U2. No boundary condition is applied on U2, so this is unknown. V2 unknown. W2, as I mentioned, we fix displacement normal to the plane. And then we can look at the third node. So U3, we know that this is restricted because that node cannot move in the x direction. But V2 is free and U3 is free and W3 is 0. So U3 is free because we have a roller support here. Okay, so this is the vector of nodal displacements, and each boundary condition, each degree of freedom has a corresponding force, right? So we need to write now 9 components of the vector of nodal forces. So that will be Fx1, and this is unknown, so this is the support force that we don't know. Fy1, again we don't know that one. Fz1, well actually we know this will be 0 because we don't have any forces perpendicular to the plane, but we just leave it there. then there will be Fx2, right? So Fx2 is the force, external force applied to node 2 in the x direction, and we know there is no external force applied in the x direction, so this is 0. Then we have Fy2, which is the vertical force applied to this node, and we know that one is minus mg. Then we have Fz2, which is unknown. Similarly, Fx3, Fy3, and Fz3. Correct? And again, we know that Fy3, which is the force, external force in the y direction in node 2, in node 3 is 0, because this is completely free. It can move, and there is no external force applied here. Yeah, so that would be 0 too. All right, so now we have the static equilibrium equation for the entire truss structure here. And what is quite interesting is that if you look here, for every given boundary condition, you have an unknown force that we need to then find out once we solve the equation of equilibrium. So how do we apply boundary conditions and loads? Once we have done that, we know that some of the forces are known, some of the displacements are known, and some are not known. So we can rearrange the equilibrium equation to look like this, where we have RC, which are the prescribed nodal loads, and the corresponding displacement to these are unknown. So dx is corresponding to the known nodal forces. And the same thing for dc. So these are prescribed nodal displacement which have corresponding nodal forces which are unknown. So these are the supports that I told you, and this is the external force that is applied. And then we don't know the displacement of the node. So these are the unknowns shown with x and x here. So if we again look back at our example, dx here are u2, v2, and v3. So these are the degrees of freedom that are open. They are not fixed, and we don't know them. So that is really the purpose of solving these problems, to find these three unknowns. But they have corresponding nodal forces that are actually known. And the same thing for DC. So these are all the known displacement. These are where we have applied some support, some constraint, and they have corresponding unknown nodal forces, which then we will determine by solving the equilibrium equation. So now if I rearrange this equation to solve it, I can write dx, which is the unknown vector of unknown nodal displacement, as a function of all the known vectors. So the RC is known, DC is known, K12 and K11, all of these are known to us. And once I have determined dx, I can put it back into that equation, and I can find Rx like this. Okay, so this is how we can solve this problem. Now, in order to obtain a unique solution to this equation, so this is the initial equation that we need to solve. You saw it in the previous slide. This matrix K11 must not be singular. So I'm sure you know that this sign means that we are calculating the inverse of this matrix. So we have to invert this matrix, and for this matrix to be invertible, it must not be singular. Otherwise we cannot invert it. Okay, we will run into problems. In reality, this is not only a mathematical definition. In reality, we can run into problems, and there are two common mistakes that bring us into that problem, which we call it singular stiffness matrix problem. One is that if you try to model a mechanism by using static solver, so this is a mechanism, right? This is a 4-bar linkage. So if you apply a force here, this will just stop rotating. Okay, so this is not a structure in equilibrium. And if you try modeling this in a software like ANSYS, you will definitely run into an error, and probably that error will be something very much similar to this, like pivot in the structure or singular stiffness matrix. Another mistake that we can make that lead us to this problem is not defining enough supports for our structure. And that means the structure will just start moving forever. So imagine here, if I just replace that pin joint by a roller joint, this support will start falling down, okay? And therefore our structure is not in static equilibrium anymore, and the software will not be able to solve this problem. If you do not believe me, I would actually strongly encourage you to model both structures and see what you get from the solver. Perfect. So as a summary, we describe what are the nodes of truss elements and what are their degrees of freedom in one-dimensional, two-dimensional, and three-dimensional. So essentially, their degrees of freedom are translation in X, Y, and Z in three-dimensional space, which is the most generic case. We learned about element stiffness matrix and structural stiffness matrix, and these were defined in the context of truss elements. We will define them in the context of other types of elements. We understood what are vectors of nodal displacements and nodal forces. We saw the FEM's equilibrium equation. We learned what are the boundary conditions and loads that can be applied on truss structures. And finally, and very importantly, we learned something that is called singular stiffness matrix, which is an error that we can get when we are doing our simulations. And this can be caused by two problems. One, that our structure is a mechanism, and second, that we have not applied adequate support to our structure. In both cases, our structure is not in static equilibrium, and therefore will move forever, and the solver cannot solve this problem. Thank you for attention.